how we roll, man. Some rock, some win, some 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 win.
Hi, my name is Loris Crow, and we are executing at Showtime. Zig SHOWTIME is a show and a community for makers. Watch the show to learn about interesting projects, and join the Discord server to share what you're working on and to collaborate with other members of the community. And if that's not your style or you're new to Zig, make sure to check the other Zig communities to find one that suits you best. So, hello everybody. It's been a while. New year, new Showtime. Usually I have a bunch of news at this point. I do have a couple, but nothing major at the moment. So let's go quickly through them so that we can give space to the speaker. So let's see. Okay, so piece of news number one is, as I said, the minor one, but is that I'm working on a blog series that I'm publishing on Zig News about making iOS applications in Zig. And right now I'm at the stage where I published 2 parts of the entire series, which is probably going to be 5 posts long, maybe even 6. And in the beginning, we are setting up the project, configuring Xcode so that whenever you build the app from Xcode, whenever you press play, it also rebuilds the Zig project if necessary. And I'm also explaining how to interoperate between Zig and Swift. But I think the most interesting part about the series is going to be later on, once we ditch completely Xcode and Swift, and we just go straight from Zig to the OS, no intermediaries. And that's mostly useful, I think, for video games more than anything else. You probably don't want to go full native to then interface with the same usual APIs that print buttons on screen and stuff like that. So that's hopefully going to be interesting for people. And I'm not the only one working on this stuff. There's also Specs, who has been, if you've watched his recent Twitch streams, he was working on a Oculus Quest demo written entirely in Zig. So he's I'm not super familiar with the details. Hopefully he will publish something that explains better how to do this stuff. But the idea is that he got the Oculus SDK and then used the DC interoperability capabilities that Zig has to write an entire VR game in Zig. So yeah, I think these are 2 interesting things that we've been working on recently that I do recommend you check out when they're published, or as we publish them, let's say. Okay, so second piece of news, this is about Showtime itself. You're already seeing it now, but I'm changing Showtime a little. I'm not going to do 2 talks each episode anymore, but I'm just doing 1 talk per episode. I'm hopefully gonna shorten the episodes. I know that I haven't been always the most precise host when it came to keeping track of time. Sorry. But the idea is that I kind of wish we could do meetups and in-person events. Handmade Seattle has been great, and the problem is that though the COVID still doesn't agree and we still have waves and stuff, so organizing in-person events is still a nightmare. So I don't know. I personally, even as the host of an online show, feel fatigued by this online stuff. So at least I'm gonna try to shorten it. So that's it. Okay, so these were the news for today. Let's get on with the talk. So let me bring up the title screen. And let's introduce our speaker. So we all have our favorite OS. For some, it's macOS. For others, it's Linux. Someone, somewhere, might like Windows on ARM, but we don't kink shame. I, for one, use NixOS, by the way. Today, today's guest likes Plan9 and decided to improve Zig's support for it. So the talk is titled Zig on Plan9, and Jacob, the stream is yours.
Thank you, Loris. Okay, so today we're gonna talking about how we can run Zig code on Plan9 and things related to that. And as you can see, both Glenda and Zero are from outer space, which I thought was a nice touch. Okay, so the talk will be structured. We'll first talk about the executable format from Plan9, and then I'll talk about the linker that links to that format, and then I'll do a demo, and then I think we'll have a Q&A after that. So first, before anything, many of you probably don't know what Plan9 is. So it was made in like the, let's say, early 90s to like mid 2000s was when like it was prime time. It was built at AT&T Bell Labs, which also made Unix, so it was like a successor to Unix. And it had lots of ideas that were adapted by other systems. So for example, UTF-8 was invented for Plan9. So was /proc, the like process file system, now on most Unixes. And as you can see in this presentation, I'm going to be clicking on different things in the slideshow, and those will just like open it. And the editor I'm using called Acme has special features that will just open things depending on what they are. So we'd also, probably the main idea from Plan9 is that everything's a file system. So like /proc, /net, you can just read and write to /net, whatever, and you can do network interface. You can just treat IMAP as a file system, and you can just do like, you can read and write to IMAP as if it were a file system. And everything is text, so they try to like stay really text oriented for a lot of things. If you want to learn more about Plan9, I would recommend this talk, and the slides will be, I'll put them on GitHub so you can look at this and search it up yourself. And this talk is more recent, and it's really nice talk, like detailing what's special about Plan9. And then for this talk, like the executable format on Plan9, the a.out format, is really similar to Unix a.out. So we can really think of it as like another Unix, but you have to be aware that it's not another Unix. Okay, so what is a linker? So a linker takes a bunch of functions, and then it can take a bunch of like constants, like in Zig you think of it as like pub_const or pub_var, a bunch of globals, and then usually takes object files and then produces an output file, whether it's like a library or an executable. But in the Zig self-hosted linker, which is written in Zig, we're actually not going to produce, not going to take object files as input, because we want it to be so integrated with the compiler for speed that all we're going to do is take globals and these functions. So we're not going to worry about these object files today, but it might be an improvement if we want to link C code to deal with object files later, and then we produce the output. Okay, so what's an object format? So an object format is basically something that a linker produces, and it's loaded by something. So like ELF object format, it's used by like Linux, a lot of BSDs, even Serenity OS, a lot of modern systems. Macho object format, which Jakub Konka works a lot with, it's for macOS. You have WebAssembly for the web. That's not loaded by like the operating system, but it's loaded by a browser. Then you have PE/coff for Windows. SpearV, it's the same thing. It's not loaded by the operating system. It's loaded like by I think it goes into the GPU. And then here's an interesting one, C. You can technically think of this as an object format because Zig can compile into it, and then that gets loaded by not the operating system, but GCC. And then the one we're going to be dealing with today is the Plan9 a.out. And if you want to look at the source code for all these linkers, you can just go to source/link in the Zig codebase, and you can just see the source code. It's pretty simple. And then, yeah, it gets loaded by the operating system. And here, the Plan9 system has all the source code for it on the system, so we can just open it up and go to the sysexec function in the kernel. And it just loads, it reads the file, make sure like it aligns this sections, then executes it. So like, the key thing to take away here is that object formats are not magic, but they're concrete things that you can read and write. Okay, so let's talk specifically about the Plan9 format. So it's detailed in the a.out man page, section 6. And the header looks like this. So let's look at it in Zig format here. So we have the magic number, which is a U32. This details just says that it is a Plan9 executable, and then details what the magic number is. So like what architecture it's for. Then we have the next few sections are size of all the different segments. So the first one, size of the text segment. So this is like how many bytes of machine code there are. The next one, size of data. So this is like how many global constants there are, like the size of all those. The next one, size of BSS. Now, I'm not going to be talking about this that much because the Zig linkers don't really implement BSS yet. So I didn't really have to deal with this yet. Size of the symbol table, pretty simple, how many bytes the symbol table takes up. And then the entry point, which is a U32. And we'll get back to that. Then we have the size of it tracks the program counter to stack pointer. It's a map of that, but we're not going to worry about that because it's depreciated. And then this one, this is the debug info, so it maps the program counter to the line count in a file. And then the last one is an entry point, but it's a U64. Now, you might be thinking, why do we need 2 entry points? Well, if you're on a 64-bit system, the entry point could be in a 64-bit address space, which means you need to use 64 to track all the possible entry points. But Plan9 was made when there were only 32-bit systems, so they didn't think of this in advance. So they just added an extra U64 at the end of the header, which you can check if it's going to be there by seeing if the magic number is for a 64-bit architecture. And then instead of using the 32-bit entry point, use the 64-bit entry point. So that's the header. So all that comes first in the object file, and all these numbers are big endian. Yeah, so then the next section is the text section. Pretty simple, it's just machine code. This gets loaded at 2 megabytes 2 megabytes plus the size of the header on x86-64. It's different on other architectures. So this is just all the machine code in the file. Then we have the data section for all the global data in the file. So this is like pub var, pub const, all that kind of stuff. There's no read-only data. It's just data. It's just you just get one data section. And obviously the BSS is not in the file itself because that gets put in by the kernel at 0 initialized memory, so we don't have to worry about that. The next thing in the file is the symbol table. So each symbol has a value, which is either a U32 or U64, depending on if we're on a 32 or 64-bit architecture. And this just says the address of the symbol. So if it's let's say it's the start symbol, well, that's going to be at the start of the text section usually. So then it's going to be 2 megabytes plus 0x28 because that's the size of the header. We have the type of symbol, so this can be text, data, or BSS, things like that. Then you have the name of the symbol. This is just an alternated string. It's pretty simple. We're not going to worry about this because this is depreciated. This is for a different architecture. And then this is our debug info, which we'll get into next. And so it's pretty simple compared to ELF, which I've also looked into. This is much more simple, but it still took me a while to grasp because there's not very much documentation, so I had to do a bit of reverse engineering. So if we look at, if we want to write this, we want to write a whole file without debug info in x86-64 assembly and NASM. It's pretty simple. We first write out the magic number for x86-64 in the header. Then we write the size of the text in big endian format. We don't have any data in this file because this is only just calling the exit syscall in the text. We write the symbol table size, so it's 8, which is the address of the symbol. Then the symbol type is just 1 byte. And then the name of the symbol _main, which is the conventional entry point name on Plan9, is 6 bytes. So that's the size of the symbol table. Pretty simple. And then the entry point, it's right here. It's 200. It's just 2 megabytes and 0x28. And then the fat header is the same thing, but it's just more. It's 8 bytes instead of 4 bytes because it could be a 64-bit system. So the binary format is quite simple once you understand it. Okay, so now let's talk about the debug info format. So it's a bytecode. So there are 4 operations for this bytecode, and there are 2 variables, and you just interpret the bytecode. So think of each of these numbers as 1 byte. So when you interpret it, you first see if the first byte you interpret is a 0, you interpret the next 4 bytes, you bitcast them to a big endian I32, and then you add it to line offset. So now, what is the line offset? So it starts at 0, and the instructions can either increase it or decrease it. And then to tell to find, let's say I want to find the line at what line is at the function main. So I just find the address in main. Let's say it's at address 2, for example. Obviously it wouldn't be, but let's say it was. Then I just go through this bytecode, and then if I see when the program counter equals 2, I find what the line number is, and that's the line number of main. And I'll give some more concrete examples in another slide. These next 2 bytecodes are just optimizations for this one. So when you have a number that's less than 65 that you want to add to the line offset, you can just write it out if it's greater than 0, and that you don't have to write out a whole 5 bytes, you can just do 1 byte. Same thing if you have something if you want to subtract something from the line count that's less than 65, do the same thing, just add 128 to it. And then, add 64 to it, and then you can just encode it, and then to decode it, you subtract 64, and then subtract it from the line offset. So that's it. These are just optimizations for this first case, where you add a big endian I32. And then if you have a number that's greater than 129, you subtract 129 from it, multiply it by the minimum instruction size, and then add it to the program counter. So this is just saying, I want to change the program counter, which is basically where I am in the text section, by a certain amount. And this part might be confusing. Why do we want to multiply it by the minimum instruction size? Well, this is just to save space, right? If the minimum instruction size is, let's say, it's 2, for example, well, think about it. If we have, let's say, our program counter offset that we want to change is 8. Well, the program counter offset will only go in size in jumps of 2. So it's going to be 8 or 10 or 6, but it's never going to be 7 because the minimum instruction size is 6. So when you're dealing with program counter offsets, you just divide it by the minimum instruction size to save space, and then you add it to the program counter, and you can't subtract from the program counter because it always increases. And then after all the opcodes, just add the quanta of the instruction size, which is another way of saying the minimum instruction size to the program counter. This is just another optimization because let's say you have let's say you have a line that's 1 byte long. Well, you would use this, and you would say you just do 1, and then after every opcode, add the minimum instruction size. So then we're just on x86 it'd be 1. So it would be line count plus equals 1, and then program counter plus equals 1. So this is just an optimization if you have a line that's also 1 byte, 1 text byte. So it's simpler. And I'll give an example in the next slide. And this is detailed in the man page itself here. And yeah, so I just had to read this a lot of times until I understood it. And there are some bugs in this. I sent in patches to the man page. They haven't gotten merged yet, but hopefully soon. Yeah, so that's the debug info format. So for our decoder, it's quite simple to write a decoder. Well, first of all, I wrote a library that I put on GitHub to just read a Plan9 executable format and parse all of parts of it, because I feel like if you're trying to first write a file format, you need to know how to read it. So this is a simplified version of what's in my reader. So basically, if our program counter is greater than or equal to the value of our symbol that we want to find the line count of, we can just break. Otherwise, we just read the first byte, and then if the byte equals 0, we just read the big endian I32. Otherwise, if it's less than 65, we just add it. If it's greater than 65 but less than 129, we just subtract 64 from it and then subtract that from the line count because it's going down. It's just two optimizations of this base case. Otherwise, we just add to the program counter this minus the minimum instruction size, and then we always add the minimum instruction size. So that's a really simple way to do debug info. Yeah. So, and this is an example. This was a random file that I found, and it had this as in the debug info section. And this is me just like manually interpreting this and writing out what all of these instructions do. I'm not going to go through this because it would take a lot of time, but the key idea is that if the program counter or the line counter is where you want it, you can just stop. Like, let's say I already went through this, but that's the key idea. Yeah, okay. And then here. Okay, so now you can find the line from like, let's say you know the symbol main is at, like, the virtual address is at 3 megabytes. So now you can find the line count, what line symbol main is at, but you still can't like display the file because you don't know the file name. This is where the symbol table comes in. So you have a few types of symbols. You have the text symbols, data symbols, DSS symbols, then you have file segment symbols, then you have a Z symbol, which basically puts together a bunch of file segment symbols, like kind of like a TRIE, tree data structure. So a sample symbol table looks something like this. You have a Z symbol, and then it's made up of F symbols, where each F symbol has a number, and each of these components references the number of an F symbol. So like Z symbol would just say the file name, and then after the Z symbol, I have it indented, but obviously it's just after it, you have a text symbol, and these are all like the same symbol format where you have the value, then you have the type, and then you have the name. We saw on like one of the first slides. Then we can say we have like another text symbol. This one's a global text symbol. This one's not. And then if it found the line number for this symbol, because it has the value, like the program counter value of the virtual address from it, then it can see, oh, I know this comes from start.zig. So then it can fully display the line. I hope that makes sense. Okay, and then next, like, we have our main.zig file. We have the main, and we also have the virtual address of main, and we can display a line from it. And we have data symbols. Data symbols, it doesn't really matter what file they come from, because they're just data. They're not, you can't like step through it. So you can just have those after. And then to use this, we have the ACID debugger, which is a debugger that's used on Plan9, which I'll demo later. So yeah, the symbol table, the way you do it is you first do the file that the symbols come from, and then you do the symbols themselves. Okay, so hopefully that made sense. That was me just going through the file format of Plan9. Now let's go into the linker that wrote in Zig. So first of all, when I was writing this, I wanted to see, are there any previous linkers that I can kind of look at to like see how this works? So there were two that I found. The linker from Plan9, and then the linker in the Go compiler, because Go, it was written by the people who made Plan9, like Ken Thompson, Rob Pike, and so it has pretty good support for Plan9. It doesn't have debug info, but it like fully supports, like I wrote a web server and it just ran instantly on Plan9 when I cross-compiled it, which was pretty nice. So let's see the linker on Plan9. It's called 6L, the asm.c file, function called asmb. So when I was reading this, they like to use very short variable names, which is nice if you're writing code, but not so nice if you're reading code. So it was really hard for me to read this. It helped a little. It helped me understand what the fat header was. But other than that, it was like like they put the magic in the text size and the data size. Like I understood that, but I wanted to understand get a mental model of how the file format worked, and this didn't really help me that much. The Go linker, it's pretty similar to that, and yeah, they have SMB Plan9, but it's basically the same thing as the C linker, and it didn't help me that much either. So I had to kind of read the man page and do a bit of reverse engineering and ask around on IRC, and people on IRC were pretty helpful. Okay, so a key point in the Zig incremental linker is that we want to be able to we want to be able to compile something and then update one single function and then rewrite the binary really, really quickly without having to change any other functions. So let's look at kind of the conventional way of doing things, where we have a text section, and we have three functions here. We have the A function, which all it does is it calls C, which is at address 6. Pretend that each instruction is only 1 byte and starts at 0. A just calls C. C returns 1. Then A just returns, so it returns 1. Then you have a B function. B function is just like a bunch of filler, and it just returns nothing. Now, what happens if we add another line? What happens if we add another nup? Well, now all the instructions after B get shifted by 1. So now instead of calling 6 would be calling into B, which wouldn't make any sense. You have to update A to be call 7. That would be really annoying, because every time we update one function, we have to update all the functions that reference that function. So a global offset table kind of gets us around this issue by instead, we have the same thing in the text section, but instead of calling C directly, it calls it indirectly through the global offset table. Now the global offset table is in our data section, and it's an array with however many. It just has the values of all the functions, and then each function has a global offset table index, which is just the address of that function in our memory. So C's index is 2, and then it's obviously we have to multiply it by 8 because that's the size of each 2 bytes plus 8 because it's a 64-bit times 8 because it's a 64-bit address space. So now, if let's say we add another line here. Well, all we need to do, now C is at 7, so now all we need to do is just update the global offset table index. We don't have to recode gen any other functions. This is the key point. This is why we use a global offset table. So now I'm going to show you the code for the global offset table. Hopefully this made sense. Basically, it's just a way of calling things indirectly. And you could use relocation to do this. I initially did that, but it got pretty complicated. Basically, the API for Zig is that you initially give it all the code, and then it compiles it and produces an output, but then it stores it all in memory. So then you can change some of the code, and then it will only recode gen what has changed, and then it will just write it back out to the binary format. So it's pretty it's supposed to be pretty fast. So when we see a new declaration in the linker, if the declaration doesn't have a global offset table index, if the index is null, then we see if our free list. So this basically says when we delete a decal, we add it to the free list. We add its index to the free list. If we have a free index, we just assign it that. Else we move up we just add 1 to the length of the global offset table, and then we give it that. And this is pretty nice. It works. It's a good way for managing our global offset table indexes. And then let's see here in our n function, when we're finally writing out the declaration, all we do is we just write out to the global offset table. We write out to the index in the global offset table the offset of the function. So instead of having to change all the instances where it's called, we only change the global offset table, which is pretty nice. And this is in the flush module function, so it's right at the end of our linking phase. All you do is use mem.writeInt, Let me see. We just write it to the global offset table. We index it at 0 to 8 to get that 64-bit address space, and then we just write the offset, and then we write it in the endian format. So that's really nice. And then when we call a function, we just use this global offset table index. So as you can see here, this is in the code gen. If we're calling a function, we just get the global offset table index of that function. And then to get the global offset table address of the function, we do the base address of the global offset table plus the index of that function itself that we're trying to call times the pointer bytes. Like that's 8 on x86-64. And then in the call function, or in the call instruction, we just we write the function global offset table address in the call. So like if you're thinking about if you wanted to see how this would work in assembly, it would be call on AT&T. It would be like call and then the address. On NASM it would be call address, and it dereferences the global offset address. And then it uses that as what it calls, which is pretty nice. So that's how the global offset table works. Hopefully that gives you a little bit more insight on how Zig tries to do incremental compilation. Okay, and as I said before, when we do the linking, we don't link everything at once. We codegen each decal individually. Like a decal, you can think of it as like a function or a global constant. We codegen that individually, and at the end we write it all out. So when we have the function update func, we're passed a function. We codegen the function, we get the code. This is just, it's literally const U8. It's just basically a byte stream. And then all we do is we put it into our function table. Up here, you can see at the top, there's a field, function decal table. Now this maps a file to all the functions that are in that file. So it's a hash map from a file to a map of declarations and the output from the function, from codegening the function, which includes like the code, the debug info, things like that. And you might be thinking, why do we need a nested hash map of like 2 layers? This is because we need to sort all the functions by their file, because in the symbol table, remember we had to have the file, like the Z symbol, the file where all the functions came from, and then all the functions after that, so that the debugger can get the right file. It's pretty simple, so we just have a hash map, and then the data one is much more simple. We just literally map a decal to a array of bytes. Incredibly simple here. Update decal is the same thing. It just does it for a non-function declaration, and then we've seen this before, but the flush module function just writes everything out. It does this using IO vectors, which are basically just a list of slices. Basically, you have a pointer and you have a length, and then like the first IO vector will be our header, so the header slice pointer, header slice length, and we keep going down. Then now we're iterating through all of the function decals. So this is the text section. We just make an IO vector with the base of the basically the output, the pointer to the output to length, and then we have a list of all these IO vectors. We do the same thing with the data. We make a new IO vector here, and all we do is iterate through it, get the code, and then make an IO vector from that. And then at the end, all we do is we write out, we do p-write vall, we write out all the IO vectors to the file, and it's quite simple. And then we have like an IO vector for the global offset table, and like the line count info and the symbol table, and that's it. So it's pretty fast. The other linkers do it differently, where they have the file literally stored in memory, and they just like seek the file and then write things to that. This is doing it a bit differently this is the way the C backend does it, where it gathers up all the decals and then just flushes them out really fast. I'm not sure which way is faster, but This one's simpler, so that's just why I chose it. In the future, if it's clear that a method of storing all the whole file in memory and then writing to it as needed is faster, we can switch to that. Okay, so I've been talking about this for a while. You want to see it in action. So as you might be noticing, I've been opening files that were in /home/Jacob, and this is not on Plan9, but as I mentioned before, Plan9 has really good support for virtual file systems. So like my home directory on Linux is mounted over SSHFS on /home/Jacob, and this will allow our debug info to actually fetch the files, which is pretty cool. So I'm going to run this command. It's going to just echo pom function main void, and we're just going to take our string, and then we're going to do standard OS Plan9. We're going to do a syscall. We're going to do the pwrite syscall, writing to standard out, which is 1. Like that's the file descriptor for standard out. And then we're getting the the pointer for the string, the length of the string, and then we're not doing any offset because it's pwrite. And I would have liked to make this just like standard.os.plan9.pwrite, but there are some x86 64 backend bugs that are going to require a lot of work on the registry allocator that are blocking this, and I didn't have time to do that before this talk. But so we're going to just write all of this to /home/Jacob/test.zig. Let's just open this to see that it worked. It worked. Cool. Okay, now let's compile it. So we're going to SSH into the Linux machine. Then we're going to run the Zig compiler, which I've already built. Build exe, that file. Then the target's going to be x86-64, Plan9, none. And we're not going to use stage 1. We're going to use our stage 2 backend, the compiler written in Zig. Okay, we didn't get any errors. It worked. Let's run it. So now it will have generated it in /home/Jacob/test. So I'm going to middle click on this to run it. And in our buffer for standard, oh, we see. Hey, Zig SHOWTIME. It worked. That's pretty cool. And we can run it again. And now the cool thing is, we can also use ray trace, which is like strace, on that binary. And we can see it did 2 syscalls. It did the pwrite syscall with Hey Zig SHOWTIME. Then it did the exit_s syscall, which is just the exit syscall value 0. So it exited. Only 2 syscalls. Okay, and now we want to debug it. So window just creates like a new window in our window manager. Command is acid/home/Jacob/test. And that opened a new debugger window in the, that opened up a new debugger window. So we can type new to create a new, and now we're at main. So we can find the source at our program counter. And if this looks like a programming language, that's because it is. Acid is a programming language, like with a debugger around it. So it allows you to do some pretty complex things, but it also allows you to just debug stuff. So as you can see, our source, we're right here. Now we can go next, and we're there, and next, and we're at the end. We can continue, and then Hey Zig SHOWTIME prints out. Now there's still a bit of work to do with debug info, but it works pretty well. So we can make a new file. It's breakpoint at main. We can set a breakpoint now at the syscall function, syscall4, and then we can continue. We're at syscall4 right now. Let's do source, where our program counter is. Boom, at syscall4. We can disassemble our program counter also. This is the disassembly for syscall4. It would be the same as doing asm syscall4. Cool. And now we can step instruction by instruction also. So it basically sets a breakpoint at the next instruction and then just runs it. So it's running through all the instructions in syscall4. And I'll keep doing this until we get to the syscall instruction, and then once that executes, it should print out Hey Zig SHOWTIME. Okay, moment of truth. Yay, it worked. So that's how you can debug a Zig program on Plan9. Now, obviously, there are some bugs with this that I have to still work out. It's not perfect, and there's no variable debug info yet. It's gonna take a lot of work. I might have to even like change the debugger because Plan9 uses stack-based like variable allocation, while Zig can use stack or register-based, depending on if they run out of registers. So I don't know if debug info has even a specification for register-based variables, so we'll have to figure that out. Yeah, and a cool thing about this is that if we instead run this in the Acme editor, so let's see, win. We can do acid test. And this is just it's the same thing, but running in a shell in the Acme editor. If we do like source main, if we click on it, it will just open it, which is pretty cool. And there's even a command for this, bsource main, and it will open it. And then we can do like stuff like bsource file pc, which basically gives you the program counter from a file location. We can do main.zig:2, and then this should open. Whoops, maybe it's PC file. Oh, sorry, it's not main.zig, it's test.zig, that's why. If we run this, which I'm doing on middle clicking on it, and it was file PC, it brings us there. We run it again. Let's see, maybe 4. Boom, yeah, we're there. So there's still some bugs, but it's working good enough for now, and I'll keep working on this. Okay, so that's the end of the demo, and then let's finish up with some bugs that I found while working on this. So I had to send some patches to the man page. So this is my patch, so that I had to write a patch for the 8.out man page, so that it would show that if the symbol value is, if we're on 64-bit systems, then it should be 8 bytes instead of 4. And then I also found like another symbol that my parser errored on because there's nothing for this in the man page, so I had to add that to the man page. And then Synap, who I asked about the fat header thing on IRC because there was no documentation for this other than the source code, so I was just quite confused about like what is this fat header? Why is it like there? Why is it messing up my parser? And then he wrote a whole patch for the kernel and the man page, which basically enabled the use of fat header, and it documented it, which was really nice. So thank you. And then on the Zig side, there were lots of x86-64 backend bugs, and I even developed the print mir debugging tool. Didn't really help me, but at least it helped Zig, so that's good. And it kind of helped me diagnose the issue, but I didn't help me fix it. Yeah. So thanks for listening to this talk. We have Glenn and Zero. The slides, when I upload them later today or soon, will be at this URL, P9Z talk on my GitHub, and the executable for parser for Plan9 is already up, called Plan9 Zig. Yeah, thank you.
Thank you very much, Jacob. So let's go on the Q&A. First of all, I have a small technical question for you before we go into the Q&A. So now, near the end of your talk, of your presentation, your microphone started clicking a little. You're still perfectly... we can understand what you're saying perfectly. The question is this a problem that you've already experienced? Do you know how to fix it quickly?
No, I don't.
You don't? Okay. Now it seems gone. Like what you said just now didn't have any click in it. It's so weird. It just kicked in like in the last couple of minutes, something like this.
Could have been my mouse. I was clicking around the screen.
Oh, oh, I don't know. Maybe. Well, now you're
Okay.
perfectly good. So never mind. I'll take that back. Okay, so first question before. For everybody watching, if you have any question, feel free to write it in YouTube chat, and I'll convey your question to Jacob. While everybody types down their questions, I think since this is your first talk on Showtime, the first question has to be, um, how did you find out about Zig, and how long ago was that?
I think I first found out about it probably in like January of 2020, right before the pandemic. I stumbled across Andrew's video at the Recruiter Center, but then I was like, I only knew like Python and a little bit of JavaScript. Like, I had no clue what it was,
Mm-hmm.
so I just kind of um, like disregarded it until the summer of that year when I learned a little more about low-level programming, and I realized I really wanted to write a compiler for some reason. I don't know why. So then I was like, but I have no clue how to write a compiler. So I read some blog posts and I wanted to like actually see how a compiler worked in real life. So I knew about of a few languages. I knew of C and C++, which I knew I did not want to read the source code of. I knew of Rust, which I also like. I looked at it, it was like so many nested directories. I knew I couldn't read the source code of the compiler for Rust. And then I remembered, oh, I know Zig has a compiler. And I looked at the Zig source code, and it was like one file called parser.c++, and it was quite simple. So read that, then I like got more into it. I started reading the self-hosted compiler source, and then yeah, that's how I learned Zig, and that's how I started contributing to Zig also, because then I had like read the compiler source.
Awesome. Um, that's amazing. So, okay, first question. I think the first question that I'm gonna ask you comes from Twitter, actually. So I posted the announcement for this episode about an hour ago, something like this, and somebody asked that. So, but you know what? I'll read the tweet to you. So this person says. I feel like I've heard a lot about Plan9 recently, but it's an OS that was most recently updated in 2003, question mark. What's the deal? And smiley face.
Uh,
So it's not an aggressive question, but they want to know
okay.
why is somebody, what's interesting about Plan9?
Yeah, so I think it's interesting because it has a lot of cool features. For example, the everything's a file system, like everything is a file taken to the next level to file systems, and like all its components compose really well. It's kind of like Serenity OS. It's like everything's in-house, so a lot of like it's not like Linux where you have to like use like glibc and then like a different program and it doesn't like all fit together, but it fits together really nicely. Like as you can see, like the debugger presented the source in a way that I can just click on it and it would open things like that, and it just worked really nice. And it's kind of had a recent like people are still working on it. There's a fork called 9front, which is what I'm using here, which has like better support for modern hardware, and it's being developed like it's actively developed right now. Even though the last recent release I think was in like from Bell Labs was 2015, but now the uh, Plan9 Foundation like manages it. I think. Yeah.
hmm So what captured your interest in the beginning was more the, let's say, user-facing, user-level features, not immediately like the binary format for executables or
Yeah.
the debug VM. Okay. Okay, let me see if there are other questions. I need to read them on my phone, on my new setup, which is a bit messy, sorry. Let's see. Um, there's a good question by World Admin. So, how's the stack trace situation?
That's a good question. Let's check it out. Just open the debugger. Let's see how it works. I did this once. It kind of worked. I need to add more like symbol debug info. I think I need to add frame symbols. But why not? Check it out. Is my screen being shared?
Yes.
So let's set a breakpoint at, or first of all, we're at the main, so let's do lstk for stack trace. Okay, no stack frame. Okay, let's go into the syscall for seems like it kind of worked.
Mm-hmm.
So it's like iffy, but this seems to have worked pretty well. So I guess it sometimes works. I haven't invested time into making it work, but definitely in the future it would be useful.
Mm-hmm. What about stack traces from Zig? Like if you hit a panic.
From Zig, I don't think the self-hosted compiler is like has enough, hasn't been developed enough to be able to call the stack trace handler.
Okay.
But I don't think it would be that much different from any other like operating system. Just interpret the binary, go into the symbol table, and then read the stack trace. I think that's how the other systems do it. I haven't looked into it that much though.
Yeah. Well, I think it's a reasonable. It's an interesting question. Also, I don't know for sure what word admin was thinking about when they asked this question, but from my perspective, it was also interesting because stack traces have been a bit bungled on M1 for a while.
Yeah.
So that was funny. Okay, let's see more questions. Is full-on 9 front support in Zig planned? So is Zig going to be supported in the long run?
I'm not sure what that question is asking. I think I'm the only one developing it.
Yeah, I think it's a question, or like, so this person probably doesn't know that we have a tier system of support in Zig. So Plan9 is going to be tier 4, tier 3.
Probably tier 4. Hopefully
tier 4.
It'll get to tier 1 eventually, but right now it's probably at the lowest tier.
Are you going to do the work to bring Plan9 to tier 1?
I mean, why not? I think most of the work will be in the x86-64 backend. I was going to mention this earlier, but LLVM can't emit Plan9 like files, so the only backend we can use is the self-hosted backend. So like the AR64 backend or the x86-64.
Mm-hmm.
So that will be probably where most of the work is. The linker is not that much code. Like the format's pretty simple. So yeah.
Okay, so just to recap for people that don't know this, in Zig, as I said, we have this tier support system. If you go to zigland.org, you can learn more about it. But the idea is tier 1 supported platforms. They're supporting the standard library knows about that platform, and we have tests that run every commit on that platform. No disabled tests that apply at least to that platform. There's a few more requirements, like I don't remember all of them off the top of my head, but as I said, like if you go to the Zig 0.9 release, for example, you can see right now each platform, like CPU architecture and OS combination, at which level of support they are. And in any case, one thing that also Zig wants to do is the idea of having a bring your own platform system, which means that even in case that there is no official support, like let's say that you're writing your own OS and Zig doesn't know anything about your own OS, you should be able to basically provide the bottom layer of the bottom layer abstraction and hopefully be able to reuse some of the functionality in the standard library through this bring your own platform mechanism. Okay, let's see, more questions. Let's see, maybe I'll read, also some comments as I scroll through. So Lucas says, the pandemic seems to have been the best thing to happen to Zig adoption and discovery. I think that's fair. Showtime was born because I was at home bored and I really did not like the conferences turning into Zoom meetings thing.
Yeah.
Okay, there's another. Okay, let's see. Matt asks, Why does Glenda's gaze bore right into my soul?
It's actually designed by the person who designed the Go logo also.
Uh,
And you can kind of see the similarities.
yeah. Another question from Lucas. Why are these people not asking serious questions? God damn it, guys! You're the old guard. Okay, so Lucas is asking, what's with the slanted roof? I don't know. They want to know about your slanted roof. Let's see. Let's see. Oh yeah, so Matt was asking also plans for Plan9 CI. Oh, and somebody else?
So
Yeah.
yeah. So I think the Source Hut. So there's a blog from Source Hut about supporting it, and it was supported once. I think the support on like Source Hut CI has regressed, but I don't think it would be that hard to bring it back. So once the compiler is self-hosting on Plan9, then I can see putting it on the Source Hut CI, and it would work.
Mm-hmm.
But it wouldn't really make sense if the compiler is not self-hosting on Plan9. It wouldn't make sense to do that because then you have to copy binaries from a different system onto a Plan9 system to run the tests, which would be kind of annoying.
Somebody's asking if they should use Harvey OS instead of 9 Front. Do you have an opinion? I'm assuming Harvey OS is another fork of Plan9.
Yeah, it's a different fork. It's like I think it's trying to do like make all the utilities in Go. I haven't used it, so I don't really have an opinion.
Okay. Cool. So, well, I think that's it for the questions. I have one final question for you, which is, other than Plan9, what else have you been working on the Stage 2 compiler? Because I know you've been present to the meetings and doing a lot of stuff.
Yeah, I've been working on the x86 backend, which is kind of related to this because it's like you need it for Plan9, but I recently like started the emit ASM, so you can like emit assembly from x86 the lowest level machine code representation in the compiler. I worked on like a debugging tool for printing MIR. I also did a bit of work on like semantic analysis. Yeah, I've worked on a lot of parts of the compiler stack. But yeah, and hopefully soon I can keep working on that. My main focus is going to be the x86 backend in the future.
Nice. Awesome. Well, thank you very much. So this was a great presentation. Thank you also for answering questions. Before we call it a day, and finally have an actually short Showtime episode, is there anything else that you want to say before we end it?
No, I think just thank you for having me on. This was really fun.
Likewise, that has been awesome. Well, thank you very much, DW, and see you on the next Stage 2 meeting, I guess. So, bye-bye.
See you.